In this tutorial, we're going to be going over tolerance stacks. Now, what I've done is I've created a tolerance stack calculator. It's an Excel file that's found on the DVD, and what you can do with this is I've already put in all the calculations and all the formulas and everything. So what you do is you are able to put in all the parts or all the features, how many of them, their dimension, the tolerance, and it will calculate all your lower and upper limits for the part, the nominal gap that you'll have in your hard stack and your RSS, when everything's computed together, the complete tolerance of everything put together, your upper lower limits, and if there's clearance. So the clearance would be your lower limit. If it's a negative, obviously there's interference. If it's a positive, you have clearance. In different cases, you sometimes do want interference, so you may want interference in both the upper and lower limits. Say if you have like a spring, you want it to be compressed all the time at a certain amount. This whole thing, what it does is it allows you to put in your parts, tell me how many, their dimension and their tolerance, and see how they fit together. Now, usually people do this by hand, tolerance stacks. I've created this calculator to include on this DVD for you because it makes it so much easier. You're able to just input your data and it spits out all your information. Now, one thing that I want to go over with this though is the hard stack and the RSS. What a hard stack is it is the hard numbers. So you can see that our tolerances here are 0.5, 0.3, 0.3. We have 2.3s. So altogether we have a tolerance of 1.4 with everything stacked on top of each other. An RSS though is more of a statistical stack, and what that means is that you're not going to get every single part at its worst case scenario put together all the time. If you go into quality control or do some statistics courses, you'll see that there's such things as like 3 sigma, 6 sigma, and what they do there is they track, how many parts per million, sometimes how many parts per billion are out of spec. So the chances of getting every single part at their worst case scenario millions and millions of times over is very rare. So what this does is it kind of gives you a statistical hard stack, lower limit and upper limit. So whenever I've been going through and doing drawings and calculations and all that, usually the RSS stack is what we take into consideration because the hard stack may be, 1, 2, maybe 3 parts per million that it may actually come into that situation where the parts don't mesh together, and in that case we just throw it away. If we were to implement the hard stack tolerances all the time, it may cost a lot more and you may be throwing away a lot more parts rather than if you're just doing the RSS tolerance and hard stack. So in general, use the RSS. If you do run into a lot of errors of like a lot of parts coming in and that they're not fitting in together, then you can take a look at the hard stack. But usually, like I said, when I make my drawings and my parts, I usually go with the RSS values because those are more a statistical approach and kind of like a statistical average of what's going on. And just so you know, what RSS stands for is the root sum squared. So it's the root sum squared of your tolerances. So what we're going to do in the following tutorials is I'm going to give you a few examples